Good afternoon. Good afternoon, everyone. I am Dr. Lee, our Senior Consultant Radiation Oncologist. Today's webinar session, I will present as a moderator. This webinar focuses on an exciting and emerging area in radiotherapy planning using the past clinical experience and modern computation tools to improve the consistency and quality in the treatment plan. Although many of us here are clinicians and planners, we all know one thing very well. Radiotherapy planning is both an art and a science, and achieving the high quality plans often depends greatly on the experience of individual planners. Today's talk will explore how we can use information from previous high-quality plans to support planning for new patients, an approach known as the knowledge-based planning or KBB. We we will also hear how deep learning, a form of the artificial intelligence, can be applied to predict those volume histogram even before a plan is generated. This is a rapidly evolving field, and today we will see an important early contribution from Myanmar. Firstly, may I invite the FARO President, Dr. Mjai, for welcome greeting.
Thank you, Dr. Ang. Good evening, everyone, and warm greetings to colleagues across Asia. On behalf of FARO, it is our great pleasure to welcome all of you to today's webinar, which is the final webinar of this year, hosted by Mstro from Myanmar. With the title of Neural Network-Driven Prostate DVH Prediction for Radixact Helical Tomo Therapy. As we know that artificial intelligence becomes an increasing integrated into radiation oncology, neural network-based DVH prediction offers promising opportunities to enhance treatment planning efficiency and quality for prostate cancer. So I would like to thank the speaker and also moderator and also discussant from the panel, as well as I would like to thank IROS and Aurora for their support throughout the year for the FARO monthly educational webinars. So as I mentioned that this is a final webinar of this year. So thank you all for joining us, and I sincerely appreciate your continued commitment to advancing radiation oncology in Asia. Thank you.
Now, may I invite Mr. President, Professor Dr. Kim Chu-win for welcome greeting.
Good evening, everyone. I'm Professor Kim Chu-win, President of MISRO, Myanmar Society of Radiation Oncology. On behalf of entire MISRO group, I would like to extend a very warm welcome to all of you attending the 37th FARO webinar. Our MISRO group has proudly been a member of FARO family since 2019. Over these years, we have consistently been inspired by the hard work, dedication, and exceptional teamwork of our members in actively contributing to FARO mission through the education, research, and leadership development. I heard this webinar will be the last FARO webinar of this year. Today, we are both humbled and immensely proud to participate in this webinar. We are especially excited to share our group's first experience in novel area, neural network-driven prostate DVH prediction for radiate helical tomotherapy. Looking at today's program, I'm truly impressed to see so many experienced radiation oncologists and physicists from the various FARO countries serving as moderator and panelists. I'm also certain there are numerous other experts among our audience participants. Following our physicist, Mr. Pyo Wei Win's presentation, we sincerely welcome everyone our esteemed panel moderators and all attendees to share your expert opinions, insights, and valuable suggestions. We believe this exchange will be immensely beneficial for all of us. Without further ado, let's begin our presentations. Thank you.
Thank you so much for Professor Kinchwe for your speech. Now we have the photo session for about 1 minute or 2 minutes.
Dear respected professor and doctors, my name is Dika from Aurora. First, I would like to thank you for joining our webinar today. And now I will assist everyone in taking our group photo. The picture will be taken twice, so kindly turn on your camera and please hold still for a brief second so we can get a clearer picture. Okay, 1, 2, 3, cheese. Once more, and 1, 2, 3, cheese. Okay, back to you, Dr. Leo.
Thank you so much. Now we will start our presentation. Firstly, I introduce our speaker, Mr. Phu Wei. He is the medical physicist. At both National Cancer Institute and Yangon General Hospital, Yangon, Myanmar. He brings clinical and technical experience in radiotherapy on modern EBRT, HDR brachytherapy, and Radiasi tomotherapy platforms. His background includes international training and multiple IEA supported program, along with the research contribution in TBI optimization and machine learning application. He was recently recognized with the Young Investigator Award from Myanmar Society for Radiation Oncology. Today, he will represent his work on neural network-based DVH prediction for prostate tomotherapy represented an important early step toward the data-driven planning in our study. Mr. Wing will represent his work titled Neural Network-Driven Prostate DVH Prediction for Radixact Helical Tomo Initial Experience from Myanmar. His study integrates public prostate data sets, automated segmentation, precision TBS dose generation, and custom design multi-output deep learning model to predict the DVH for the prostate bladder in rectum. This represents the first initiation of its kind within our local context. Without further delay, please join me in welcoming Mr. Phu Wei for his presentation on neural network-driven prostate DVH prediction for Radiasi helical tomotherapy. Mr. Phu, the screen is yours.
Good evening, distinguished colleague, respected member of FARO and friends across the region. My name is Phu Wei, medical physicist at the radiotherapy department, Yangon General Hospital and NCI. It is an honor to share with you a project that is deeply meaningful to our team in Myanmar. My presentation today is titled Neural Network-Driven Prostate DVH Prediction for Radiasi Helical Tomo Initial Experience from Myanmar. This is more than a technical study for us. It represents a milestone. The first deep learning and neural network-based DVH prediction have been integrated with Radiasi Helical Tomotherapy platform in our clinical environment. With this project, we are stepping into the same scientific conversation as center across the region, and we are showing that Myanmar is ready to contribute to the future of data-driven radiotherapy. Thank you for being here. Let me begin. Before we dive into the deep learning part, let me briefly review the tomotherapy platform. Tomo is a CD-integrated image-guided IMRT system. It combines a linear accelerator with a fan-beam helical CT. The term Tomo originally came from the Greek word meaning slide. indicating that the treatment is delivered slide by slide using a modulated fan beam. In our institution, we use the accurate precision treatment planning system for Radixact. This system allows continuous gantry rotation while the couch moves steadily forward, creating a helical treatment delivery pattern. Here is our machine at the NCI. Here you can see the core geometry of the system. The gantry rotate continuously at a phase speed ranging from approximately 11.8 to 60 seconds per rotation. At the same time, the couch move along the y direction with speed ranging from fraction of a millimeter per second up to around 40 millimeter per second. Radiation is delivered through many small beamlets whose intensity depends on how long each MSC leaf stay open. In simple terms, tomotherapy delivers modulated radiation in a smooth helical pattern. Historically, radiotherapy plans depend heavily on the individual planner's case and experience. Plans were essentially handcrafted. This was labor intensive, and naturally, there was a lot of variation between planners. We didn't have a systematic way of using high quality plan, aside from a few templates. Those prescription was largely based on intuition. The real challenge was this: planners didn't know what DVH cap were realistically achieved for a new patient. As a result, consistency and efficiency were difficult to maintain. This brings us to a key question. How can we make better use of what we already know? In radiation therapy, we have large amount of knowledge stored in past patient data set like CT, control, and high quality plans. Deep learning provide a natural way to learn from this history. By predicting DVH before planning began, we can improve plan quality, maintain consistency among planner, and reduce the time spent on trial and error adjustment. Knowledge-based planning emerged as a systematic method to learn from historical plan. The basic idea is simple. Take many high-quality plan and learn the relationship between anatomy and dose. Then, for a new patient, use that knowledge to predict achievable DVH cap. This concept traced back to early work by China Vanish in 2011 and commercial implementation in 2013 and so on. Especially, KBB formalized what we experienced planner already do mentally. Instead of relying purely on intuition, we now rely on data. But in this AI age, we have to take care about the data that we use for the training. If we use the low quality data, the garbage in, garbage out, your result will be not much useful since you didn't have that quality data initially. Clinically, KBB acts like a digital expert. It looks at hundreds of previously treated cases and give guidance on what bladder, rectum, and femoral head dose are realistically achievable. KBB hair flag, outlier plan, improve interplanar consistency, and reduce workload. We can think of it like codifying the experience of many seasoned planner into a form that assist everyone. So there's another topic that we have to highlight for this work. The first one is knowledge, and the second part is the deep learning. So DL is a final AI pattern automatically learning the data set by its own. If traditional programming is all about telling the computer exactly what to do, deep learning is about showing the computer many examples and letting it learn the underlying pattern. Clinically, this is similar to how a resident began better after seeing many cases. Deep learning is particularly powerful in RT because anatomy and dose relations are complex and nonlinear, as you already know. These are precisely the type of pattern DNA can learn very effectively. In our workflow, we use the Volo Ultra TPS, which has played a central role in this work. The optimization engine use limited memory algorithm, which comprise with two separate algorithms underneath. The first one is fluence convolution broadband algorithm and the Colescone convolution superposition algorithm. The system usually converges within about 60 iterations. To put that into the perspective, like you can achieve your final objective in a matter of seconds. The workflow is simplified, no longer need to set detailed overlap parity or complex weight structure. The software include automatic pitch selection and beyond estimation tool as well. So in here, this is the typical optimization curve in theory. Most of the case, we are trapped in the valley of local minima, which means we cannot achieve our final objective for a few iterations. So we have to run for like 15 or 20 minutes in some vendor provided TPS. In this case, we can achieve global minimum in a matter of seconds by the Volo Ultra TPS. This is the provided prostate cases with the Volo Ultra delivery performance. For an average, we got like around 3 minutes for the prostate. So in the classical Volo TPS, we have to give like 3.6 minutes for the prostate for the delivery time. So it reduces about 90% in the being on time. So here's a bit of literature study. Studying from 2011, this is the early case that they are studying for the IMRD KBB plan library similarly via benign view mutual information. So for the clinical key finding is that within 2% we can accept, we can achieve the optimal goal. For the OAS pairing, D50 is reducing to about 25%. So it's clearly show that in the early phase, we can obtain a suboptimal plan generated from the KBB. Followed by the 2011, they use a OAL PDV overlap model, and their script is to reduce the main dose asset variability for all OAL with major improvement for parotid gland and retin, and most dosimetry reported better quality and efficiency for the plan. For the 2013 study, it is the multi-institutional traditional KBB shared plan database. It showed that knowledge base improve PDV homogeneity and reduce OAR dose significantly for the retin, being superior in 40% of the cases and equivalent in about 54% and inferior in 6% for the retin. In the year 2017, for the head and neck dose prediction, they use like Balsa-based automation. And it also predicted the DVH across 6 treatment sites with low mean absolute difference compared to clinical plan. And sometimes it outperformed or matched other LSP method. The same for the prostate KBB in 2017, they predicted for the redundant dose and using the automated scripting. For the retin, they got like reduction in 5.6 grade on rollout, improved B40 and V70 range related to manual plans. So we can identify is that their study is optimal manual plan. In 2018, there's a review of the traditional and machine learning-based KBB. It summarized that KBB typically maintain PDV metric while reducing the OER doses. In the meantime, it reduced the planning time and variability and need for larger prospective DVH data sets to emphasize. In the year 2023, they started to use 3D CNN convolutional neural network for Boser-wide dose prediction. This kind of method is computationally intensive. So their key finding is that for the dose prediction error, mean Boser error is less than 3 gray. DVH accuracy for the target OER metric within 1 to 3 gray difference from the clinical plan for DMIN and DMAS. D95 depending on the structure. So it demonstrates the clinically viable deep learning dose prediction. For the final study in 2025, they have done with the fully automated up to damn disease site with a clinical acceptance rate of 88%. A few minor adjustments done with the 98%. So dosimetrically, PDV 95% and OER tolerance metric met the institutional guideline in nearly all cases, showing reliable automated KBB performance. Let me now walk through the methodology that I've been working on. Initially, I have used the TCIA public data set with about 131 patients initially. When I look at the data for these 131 patients, I have to resample back to the 512 by 512 for the TPS input, since the data provided doesn't meet our default resolution setting. So after resampling and post-processing, the final sample size that I got in here is 78 patients. These 78 patients are then imported into our Volo Ultra TPS. I use the same prescription for all these 78 patients, and then export the Diagon RT plan into the 3D slicer for the DVA CSV extractions and the RT structure set as well. So the environment that I use in here is the Python for the resampling, downsampling, and for all the DNN training. For the DNN, particularly I'm using the feed-forward neural network, which are expecting to input multiple input and the expecting to have multiple output simultaneously. And the metric that I expected to be like MAE and ABC, since the case is in here is regression. So my main goal is to get like prostate, bladder, radiant DVH, simultaneously while I'm importing the 3 input. So here's the overview for the method. The original data set is from the NIH TCIA data set, and the external validation, I use their cohort of about 5 patients. The TPS that I use in here is Volo Ultra TPS 3.5 version, Razor platform, and for the DVA CSV generation, I use 3D slicer 5.8.1, and the Python environment is 3.12.3. The data set consists of 131 patients initially. After resampling and post-processing, we ended with 78 usable prostate cancer cases. For each patient, DVH for bladder, radiant, and prostate will sample at 330 dose point. Additionally, each patient had a 24-dimensional feature vector combining clinical and dosimetric parameters. We use the clinical a classic 80-20 split, which is 72 patients for training, and the 16 patients for the testing. Here you can see a snapshot from the Python environment. I have loaded 78 patients with a 330 dose point. This is the 80% of the training site, and this is the 20% for the testing with the feature beta of 24. These 78 resample datasets were imported into Precision TBS version 3.5. Auto segmentation was performed, and planning was done with a uniform prescription approach to maintain consistency. We export diagonal RT structure, RT dose, and the RT image. In the screenshot, as you can see in here, this is the prostate auto segmentation window in the Volo Ultra TBS. So I use the auto segmentation since when I'm using the resampling, the structure are not the same as the original data provided at the DCIA. So I have to remove these original structure and then based upon the new sample 78 patient with the prostate bladder redden by using the auto segmentation. In the down screenshot, here is the typical DVH that is generated inside the DBS for this study. In here, for the ground truth data generation, the initial optimization is done with the median resolution in here. And after the satisfying DVH achieved, I switched into high resolution. The interval between the initial optimization and the final dose calculation was done in about 33 seconds, which is pretty nice in terms of optimization by the vendor. So the model that I'm designed is a multi-output neural network using the Keras functional API in the Python environment 3.12.3. A multi-output network works like a brain. Early neuron learn general feature from patient data, then the signal split into specialized neuron group, each producing a different prediction, tumor type, race, or therapy response simultaneously. So a dense layer is in here, a fully connected layer where every neuron is connected to every neuron in previous layer. The model architecture has a shared encoder followed by 3 organ-specific decoder branches here. For bladder, rectum, and prostate. The shared encoder consists of dense layer with ReLU activation, L2 regularization, batch normalization, and dropout, mainly to prevent overfitting. Each organ branch output a predicted DVH cap. The entire model simultaneously predict all 3 DVH for a new patient. In here, I would like to highlight a bit about the dropout, L2 and batch. For the dropout, it randomly turns off the neurons so the model cannot memorize patient by patient pattern. For the L2 regularization, it penalizes overly complex connection. Batch normalization simply stabilizes the landing pattern. In here this is the pictorial overview for my architecture of the DNA. This figure showing the feed-forward DNA layer. So here is the three input that I've been using for the rectum, bladder, and the prostate. There's a multiple hidden layer. The output that I expected is the expected DVH for each structure. Finally, I will use a monitoring metric such as error difference between predicted and predicted output and actual output. So it is not like the F1 or recall precision. It's basically the difference between these two curves from the TBS and the prediction of the DNA. Here, this is the final goal to achieve the bladder, radon, and prostate DVH at the end. For the model training, I use the Abdon optimizer with a learning rate of 5 into 10 power minus 4. We apply a weighted mean square error loss function to balance organ contribution. Mean absolute error was used as the monitoring metric. Early stopping with 25 epoch patient prevent overfitting. Training ran up to about 250 epoch with a bedside of 16. You can think of it like reading a book for the epoch. One epoch means reading the book once. So the model usually need many epochs to learn well. Early stopping means you stop training as soon as the model stop improving. So it doesn't start memorizing the data, which is overfitted. Additionally, the model converts smoothly without sound overfitting. You will be seen in the next coming slides. Once the model was trained, we generate DVH prediction for the head of test set, which is 20% of the 78 patient. One issue with directly predicted DVH is that raw neural network output are not always perfectly monotonic decreasing, which is clinically required. So after prediction, we apply a monotonic enforcement algorithm to smooth the curve, ensure they decrease with increasing dose. It maintains the clinical realism. For the evaluation of the model, our model does regression, not the classification. So if predict continuous DVH gap, the metric like accuracy, precision, recall, F1, confusion metric doesn't apply here. The performance of the model that we measure is two then with the MAE and the ABC. MAE is the average difference at each dose point. ABC is the integral of the absolute difference, reflecting overall agreement. So imagine shading the area between the area and the rear and the predicted bladder DVH. The side of that shaded area is the ABC. Larger the ABC, the poorer the prediction performance of the model. So we expect to have like small ABC value in here. Another metric that I use is mean dose to further evaluate the dosimetry accuracy. So mean dose value will compute for both predicted and true DVH using this cumulative DVH based definition. And also I have been added to measure the mean bias, standard deviation of the bias, MAE, root mean square error, Pearson correlation coefficient as well for all three structure. This is the model loss plot over epoch, or we can say like learning progress graph of the DNN that I have been building. So this plot shows the model training and validation loss curve over the epoch. So we already know that one epoch means reading the book once. In this case, learning the entire data set for the once with a bedside of 16. So the loss tell you how bad the model is doing. Higher loss mean more mistake. Lower loss mean better prediction. The training loss plot show a good convergence with the blue line. The model has learned as much as it can, and the more training won't help without overfitting. So we see stable convergence with no major sign of overfitting, suggestion that regularization strategy will affect it in here. So how can we detect the overfitting of our model? We can simply see it at the orange line right here. This is the validation loss. The data that I use for the validation loss is 20% of the original data. So if our model is overfit, the validation loss curve will not be acting like the training loss. It will be something revert along the entire learning process. So we have a good convergence in here. Again, here is the 20% hold-out test for about 14 sample cases. I cannot put all the DVH for all these 14, so I grab around 3 patients for this case. Visually, you can see that the truth and the prediction curve are nearly the same for all 3 structure for the 20% of the whole test. Statistically, we can see the bladder prediction are reasonably close with a bias of 0.29, nearly 0.3 grade. Error moderate, MAE, we got 0.88, and the correlation is strong. R is 0.8 nearly. And so the model predict bladder dose fairly well. Bladder prediction are strong. Thought variation is higher due to the shape and volume variability, as you can see right here in the box plot. For the return prediction, it has a slightly higher variability related to the mean, meaning the model doesn't explain return dose variation well despite moderate correlation. Return is more variable anatomically, especially with the anterior and posterior deformation. So the result is expected. For the prostate, the model predicted very accurately. Bias is nearly 0. MAE, we got like 0.07 grade with good correlation. So the model predicted prostate dose very reliably. Prostate prediction are extremely accurate due to low interpatient variability and fixed target dose pattern. Overall, the model performance best for the prostate target and the bladder with a moderate performance for the return, consistent with its more variable anatomy. In the right side of the plot, you can see that for the bladder, the bias between the predicted and true mean dose is about 0.46 grade. Overall, for all these structures, the difference between the truth and the prediction value are not so different. Here is the statistical analysis for the 20% hold out. In the y-axis, the difference between the predicted and true value, which is normalized with the 100% of the prescription. So visually, you can see like around 4% difference between prediction and the true value for the bladder. Around 2.08% for the retin and the 0.3% difference for the prostate. So by looking at the blend element plot, difference from the prescription 100% dose, we got maximum of 4% for the bladder, around 2% for the retin, and the 0.3% difference for the prostate. Here is the cumulative DVH for all the true versus predicted average DVH with the one standard deviation for the 20% of the whole test case. The band right here is the one standard deviation for all the 20% of the whole case. I have been split this structure into each diagram. As you can see right here, we are expecting to have like less than 4 or less than 3 for the ABC. We got for all these structure with maximum of about 0.6 for the bladder 0.5 for the rectum, and the 0.1 for the prostate. What does it mean? It means the difference between the true calf and the prediction calf are not so much difference. The area between them are pretty tight. But as you already know, the variation among the patient for the bladder and rectum are pretty obvious. So in this case, for the rectum, we got a difference right here, and for the bladder, we see the difference in here. For the prostate, there is no much difference between the target structure for all their patients. So we see a pretty tight difference curve in here. For the cohort, which is the external validation of about 5. So the data set contains 78 patients from the public data, and the external validation set out about 5 patients. In the box plot right here, you can see the mean absolute dose difference for the bladder is a bit wider. That means the variation among these 5 patients are dispersed. Median with the prostate, the difference of about 4% for the mass, and the rectum, we see that ranging from 1.5 to 3.7, something like that. For the external validation of the Mendel's comparison, in here you can see the difference between the truth and the predicted value are adding the same phenomenon from the 20% holdouts. Expect from this, prostate have a little bit lower than the true value, with about 1.54 grade lower than the actual value of the data set. Here is the same DVH data generation for every DVH with one standard deviation for 1GH cohort. We got like ABC with 0.9 for the bladder and 1.07 for the rectum. The difference is about 1. The ABC metric is about 1. That means the area between the predict and true value a bit difference, but we can still accept this kind of difference since our sample size is pretty small compared to the original 20% holdout. So it will be stable if we add more data into the cohort. So this is due to the smaller sample size. So in the main dose difference, we see in the previous graph, there is around minus 1.54 grade, which is due to right here. This one right here. And ABC is we got 1.7. The same blend element plot analysis was applied here for the bladder. Measurements of about 5% difference between the predict and the TPS with the prescription. For the rectum, we got 3.7% difference. And for the prostate, we got 1.7% difference. For the clinical implication, there are several clinical implications. We can predict plan quality before planning even begin. The system can flag suspicious or suboptimal plan early. Interplanar variability can be reduced. Difficult cases gain objective data-driven guidance, and the overall planning efficiency improved by reducing the trial and error iterations. The limitation that we face in here is that as with early stage study, there's limitations. Our data set size is relatively small. More diverse patient anatomy will require retraining or transfer learning. The model predicted DVH, not full 3D dose distribution. It also doesn't yet account for planner-specific technique difference or control variations, since I use the auto-segmentation tool from the TPS. Finally, prediction assumes that round two plan are high quality, so more accuracy depends on the input data quality. In the future, we plan to expand the data set, include additional organs such as benign vat, small bowel, potentially extend the approach to the other treatment site as well. Another direction is predicting full 3D dose distribution, although that requires significantly more computational power. Ultimately, we aim to develop a tool capable of generating optimization parameter and the integrating seamlessly into the clinical workflow. To summarize, KBB planning and deep learning offer powerful tools for improving RT plan consistency and quality. Our model can accurately predict DVH for bladder, rectum, and prostate, supporting planner and reducing the workload for the physician as well. With further development and larger data set, this approach has the potential to become a valuable companion to clinical planning and quality assurance process. Here are the references used in this study. These include foundational work on deep learning for radiotherapy dose prediction and the dataset source for the cancer imaging archive right here. Some of the snap from the literature that I have been described earlier. In the code editor for the redden, this line is the truth. This line is the prediction. You can see the pretty obvious difference. And the AVC should be greater than 2 or something like that in their initial KBB implementation one. And here as well. In closing, this project is more than a capable of predicting prostate DVH. It is a sample of what is possible when innovation is driven not by resources, but by commitment, teamwork, and the desire to deliver better care. I'm deeply grateful to the FARO for giving us the platform to share this journey, and I hope our experience encourage other emerging centers to explore how AI can support their patient as well. Thank you very much.
Thank you, Mr. Fu, for this very informative and forward-thinking presentation. It is encouraging to see such innovation from Myanmar and to witness how AI and KBB will help improve plan quality, reduce variability, and support our clinical outflow. Now we look forward for panel discussion. Dear audience, if you have any question to ask, please drop to the message file for your questions. Firstly, may I invite the Dr. Angkai from Yangon General Hospital, Myanmar, for his comments and for your comments and suggestions.
Thank you, Dr. Leong, for inviting me. Good afternoon, distinguished colleague. It's a privilege to join today's session as a panelist. The presentations we are discussing about reflection an important direction in radiation oncology. KBB. KBB is the leveraging data from prior treatment and emerging computational method to support more consistent and informed planning decision. As clinicians, we already recognize that anatomical variability and planner experience can influence on plan quality. So any approach that systematically assess the achievable dose volume relationships has the potential to enhance the plan reliability, assist in clinical decisions, and also improve the overall quality of the care. So today presentation represents an early but meaningful step toward the such concepts into our clinical environment. Secondly, I would like to thank my colleague, Mr. Pyo Ring, for your insightful presentations and advancing work in this emerging area. Today's topic is a little bit quite challenging for radiation oncologists because of a lot of time of the medical physics and other statistical terms. But in this AI era, our radiation oncologists need to familiar with this integration of AI technology in radiotherapy field. So I would like to offer a little comment from clinical point of view. Number one is the understanding of achievable DVH before initiation of the planning can assist in the realistic expectation of target coverage and OER sparing. Regarding about the workflow implication, by using this predicted tool, we can reduce the planning time and we can overcome the liver intensive issue. Another comment about is regarding to the quality assurance. A predicted model provide as an additional layer of the quality assurance. We can identify the plan that can deviate it from standardized ones. And then, so by using the predicted model, we can also reduce the interplanar variations and also support more uniform treatment standard. Yes, this is from my opinion. I will like to back to Dr. Liang.
Thank you, Dr. Onkar. Now, may I invite the Dr. Ari from Situ National University Hospital for your suggestions and experience.
Okay, thank you, Professor Leong, and good afternoon to all of us. Thank you, Dr. PYI, for the presentations. It's a very nice presentations. What I have in mind, I would like to ask your opinion. How will this, do you think, how will this affect the practice of the daily routines? For example, if you have a prostate cancer and then the radiation oncologists do the control, and then will you make, will the plan is, do you plan to do all of this neural network for all of the patients, or is there any some patients that you cannot do this method? And then if you can do this method, what will you, after you do the DVH prediction, if it is okay, then you will proceed with the plannings, right? The true plannings. Until what criteria that you will have the satisfaction of the planning? Do you will push the planner to have the similar as the DVH prediction, or is there, for example, if you cannot achieve the same with the DVH prediction. When will you stop? And for example, if the DVH prediction didn't as you expected, what will you do? Will you ask the radiation oncologist to do the recontour, or you will or maybe you will think to about something else? I think that is what I would like to ask your opinion about it. Thank you.
Okay, Doctor. For your first question, this study is the initial study. The ultimate goal is to have a suggestion for the planner with an optimization parameter at the end. So in this phase, I can only be showing the planner and the oncology as well with the predicted DVH. That is the first question. So in this phase, I cannot support the planner with the optimization parameter based on the prediction. So this study is just to show you the DVH. The early case is something like in the commercial software rapid plan. It showed a variable band along the your structure that you want to put. They call it like multi-criteria optimization or something like that. So the ultimate goal is to get the optimization parameter at the end for your first question. For the second one, if what we gonna be doing if the DVH doesn't predict pretty well for the oncologists? Do they need to be recontrolled? No, they have already gained the experience in the contouring. The problem will only be arise in the model training, because I have trained the model with the 78 patient. If I train the model with hundreds or thousands of the patient, the model can learn perfectly. So like reading a book, if you read one reference, you can only be seeing a thing or the data that you have been learned from one book. So if we have multiple patient, multi-institutional data, then the model can predict precisely in the entire data set for the new patient coming in. So there's a struggle also in the commercial software also. When you switch from the Europe patient database into the Asian, there's a struggle in their scenario as well. I think the mic answers your question.
Yes, and do you think also that the protocols, the clinical protocols, will affect all of this? For example, maybe the bladder protocol or the rectal protocol from the clinician will also have an effect for this. So I think we need to, I agree that we need to have a multi-institutional learning experience. Thank you, Professor Bayao. Thank you.
Thank you, Dr. Ari. Now, may I invite the Associate Professor Daisuke for your suggestions and experience.
Okay. Oh, thank you for great presentation. So your talk on AI-based DVH prediction for prostate cancer was very educational. So we don't have tomotherapy at our institution. So I was really impressed by plan quality of tomotherapy is very high. Since we are in the AI era, so I think it is really important for medical physicists to get involved and to think all the way through to building tool we can actually use in the clinic. So I have two questions. So at first, your trial is predicts the prostate rectum bladder DVH. So for prostate cancer cases, so there's some risks, so high risk, so medium risk, so low risks. So in this case, is all includes high risk. So because for prostate includes the CTB. it is one first question. So how do you think about this one?
For this case, I use the auto segmentation provider structure like prostate that it doesn't have the CDB or PDB. So it is a
Okay.
primary prostate.
Okay. Okay, thank you very much. So in the clinical, so in Japan, so low risk or so medium risk, so includes half of the or so part of the prostate for the CTB. So it is so difficult to predict the dose distribution or DBH. So okay, I understand. So the second question, so is this, how do you think about the future plan with plan optimization parameters generation? So you said, so do you have so the detailed idea?
For the optimization parameter, I have to add another feature in the training set along with the optimization parameter for each training patient in the initial phase of the DNN implementation. So in the 80-20 split of the primary data set, it doesn't include the optimization parameter data frame along with the Tangon RT structure, RT image, and the RT dose file. So you can include that as well with a CSV file or better file in the initial phase. So in that way, you can train your model along with the optimization parameter, and you're gonna have to make additional prediction branches at the DNN in order to give you the optimization parameter as well along with the DVA. So we can implement that.
Okay. Oh, it is a so good plan. So thank you very much. Thank you very much.
Thank you, Sushi Professor Daisuke, for your suggestions. Mr. Fu, there is the one message in the message bar. How was the validation done?
The external validation is external validation is done with the original data set as well. And the external validation was done with the 5 patients from our center, and the 20% whole of test itself is the validation here. Sorry. Here. So this is the primary validation of our model inside our public data set. Originally, as you already know, 80-20 split, which means 80% of the data that I'm using is going to be in the training pipeline. So the other 20%, that doesn't include during the training phase. So the model doesn't see the pattern or the feature from these hold-up test cases. This is the first validation of the model performance. Another is in here. This is what we call a standard validation. So it doesn't include among the 78 patient, among the 80-20 split. This is this train question for the model performance. So there is a 2-layer for the validation.
Another question is that may I know, do you use the single image per patient at a certain time, or do you use the sequential information for the patient? Is there any dose impact relationship noted in the model as at 60 grade prostate, or do all patients provide 60 grade as those are different for different patients. Is there any more better model like LSDM?
Okay. In this case, all these patients are expected to be given the same prescription. The scenario in the KBB is that even with the commercial software, we have seen a struggle with the different prescription among each patient, among each cancer type. So like in a scenario for the commercial software, you have to run again for your own specific group or the prescription. So you have to train again for the new prescription for the new tumor type or the site as well. In this case, I use a single prescription protocol for all the 78 patients originally trained for the ground truth data generation. So if I got the different prescription for the same prostate, or if I got the additional node stretcher, I have to train again. It also have the struggle with the commercial software. So since the model learn what we've been training, so if the model doesn't train with this kind of pattern, we have to train again.
The last question is how does the DVH mutation from the UN network compared to the manual network? Compared to manual plans generated by experienced medical physicists in terms of the QAR sparing?
So for the oil sparing, the model learn, as I have been mentioned earlier in the early slides of this presentation, garbage in, garbage out. So for the ground truth data generation, we have a typical standard DVH pattern for each organ structure with constraint, as you can see in the DVH snapshot in the early slices here. Let me show. Here, these are the goals. So it means we have to train a model with a standard or the acceptable clinical DVH pattern, and then the model predict these data. The second thing is that if you don't train the model with the LRO principle for all the organ, then your model can predict you and give you the clinical acceptable range. So for the OS sparing, initially you have to be spared before the model start training in the ground truth data generation, which means in the TPS for the model training. So the data should be a standard as much as possible in the early phase before training begins.
Is there any question? Okay, one question from our Professor Mo. From the clinical standpoint, how do you envision DVH mutation supporting the decision making before planning?
So there's a 2% for this DVH prediction will support. The first person is the oncologist. So the doctor will know, okay, my case cannot achieve that, or it can be achieved easily, or maybe it can detect the outlier. Even the DVH prediction has the error. That error may flat out that, okay, we have something strange with our pattern. Do I need to look back to our contouring? No. maybe with the senior oncologist, it doesn't need, but as a safety barrier, we can still look at the contouring first, and then, okay, my contouring doesn't have any issue. Maybe the planner should be aware that the DBH pattern will be like this. So the prediction will be support to the 2%, the first for the owl and the second for the planner as well. So the planner may have the aware that, okay, the pattern will be like this. Maybe we can try a bit more than the prediction. Yeah, this is kind of the support from this prediction. What do you do?
Is there any questions or suggestion?
Yes, I would like to make a question to Mr. Kyo Win regarding about the patient subtype. Are there any patient subgroup such as those with large prostate or prior surgery patients? Your prediction model may be less reliable or may be affected. Thank you.
Sorry, can you repeat that?
My question is, are there any patient subgroup such as those with large prostate or prior surgery where your prediction model may be less reliable or may be affected?
I have to train again. So the model only train with a simple structure, as with the early observer, because as a learning phase, we have to simplify as much as possible to know what is the relationship between the KBB model and the data that we insert. So basically, for all the KBB A floor, we look at the prostate first and then complex one less, like head and neck case. For the additional lymph node or the additional structure, we have to train again. Yeah. So you can easily apply this model right away.
Thank you.
Okay, thanks you. It is time for their closing remarks. Firstly, foremost, I would like to express our sincere appreciation to the FARO for organizing this webinar and for continuously providing a platform that promotes the knowledge sharing, collaboration, and scientific advancements access across our region. I would like to extend my heartfelt congratulations to FARO President, Mr. President, and especially to Mr. Phu Win for his excellent presentation. This work represents not only a strong academic contribution, but also a meaningful milestone as the first reported experience from Myanmar in this rapidly evolving field of AI and radiotherapy. I would also like to sincerely thank our distinguished panelists, Dr. Amkhai, Dr. Ari, Associate Professor Daisuke, for their insightful comments and rich discussion, which added depth and practical perspective to this session. Finally, I would like to thank all participants for your active attendance and engagement. I hope today's webinar has been both informative and inspiring, and that it will encourage further research and clinical application of artificial intelligence and radiotherapy. Thank you very much, and I wish you all good health and continued success. Bye-bye.
Thank you. Bye bye.
Thank you.
Thank you. Bye-bye.
You.
Bye-bye.